Okay, good afternoon. Let me uh, start my slide. Okay, so we are discussing about this overfitting of the data while building a decision tree, and while particularly when you are uh, trying to get almost the full tree. I mean, we are trying to get a consistent hypothesis. In such a case, even if it is not consistent, also we are trying to get the maximal fit over the training set, and by doing that, what happens that if there are noise in the data, or even if your data is also little compared to that, uh, the model complexity, because sometimes you can have a very complex model, so with that little data you can fit exactly with that little data, but no, that is not actually representing the process by which the data is generated. So the process might be a simpler model. So by choosing complex model itself, no, your model selection was wrong. So though your training data fitting is almost error free, I mean, you have a very low training error, uh, still no, you will get higher generalization error in that case. So that was the kind of situation, and we considers in this case there should exist another model, though its training error is higher, but its generalization error would be low. Ultimately, our objective is to keep the generalization error also low. So both training and generalization error should be low. That would be a good indications of a particular model. Now, because generalization error is also estimated on a particular set of trainings test samples. So one typical example, if I give you with respect to this, if you remember that rectangle learning situation, and you can see that with respect to the previous example, there is one particular sample where you will find that uh, this one. So let me use the pen. Right. So, for example, this sample, as you can see, it is of negative level, and it's usually with the arrangement one can understand that it may be an outlier, or it may be an erroneous sample within that, because of the leveling may be erroneous. Now, but still, now if you try to uh, get a decision tree which would also like to satisfy this constraint, which means you have to grow your tree. So this node was earlier pure node. When you are forming a decision tree at certain point, if this sample was positive, then this node, after this splitting, this node, both the nodes at this side and this side. So every splitting will have will divide a set into two partitions here. So both the partitions would have been pure, but now since it is negative, so this will be still impure, and you may go ahead with splitting this node further, and that means you can grow the tree longer, you can increase the depth and try to fit each and every data. But you will most likely this scene is a overfitting, because no, if you are trying to use it for unseen data, then you may get higher error in this case. So this is one just schematic example of this particular type of uh, data. So I hope this is understood. So these are the splitting which takes place. If you can see that if I grow it, suppose this is the first splitting attribute 1, then again this is a second splitting, again the same attribute. We are repeating because this is a continuous valued attribute. I mentioned this earlier. So ID3 algorithm it needs to be modified with respect to continuous attributes. And then, of course, here you can see that splitting takes place against this attribute 2, this value. And so this part is pure node after splitting. So you need to expand this, as I mentioned. Maybe either the splitting is here or here. So maybe we may consider, say, next point of splitting is here. So this is a pure node. So once again, you are going to split this node, and there you may find here is the splitting. And then you are going to split this region, right? Because the other region is pure. So here you may have 3 intervals, because it's a continuous interval. You may have in the same level you may have 3 splits, and finally you can get this kind of tree. Or you can consider, once again, it is split, if every binary split is considered, and with another 2 levels you are splitting. So you can see that with that you are fitting the data completely with respect to the level. So that means your decision tree is making the training error 0, right? And the tree it has become quite deep. That means you have increased so many levels while growing the tree. So, but that is not desirable. I mean, because this kind of tree, as I mentioned, that that sample itself, if it is noisy, so the splitting of that node will actually make many situations also, unseen situations will label wrongly in that case. So these are the 2 things. One is that if there is noise in training sample, so let us have one particular example. With respect to the decision tree, I have given that example with respect to the rectangles. That's a figurative example. Let us consider the same kind of data set and consider these particular data. So that sunny, hot, normal, strong, no. So if I consider the earlier tree, so this is the earlier tree. So what would you find that will this training example be satisfied with this tree? Can you tell me? Is it consistent with respect to the tree you developed?
No, sir, not consistent.
Yeah.
No, sir.
So where it is failing?
Sir, it is giving answer yes, according to the
It is
decision
giving
tree.
answer yes. Yeah. So I think it is coming to this position. Say outlook sunny, then humidity normal. So it is satisfying these 2, right? And then it will basically following this chain of decision. First outlook will be tested. Then because it is sunny, then humidity would be tested. So the decision is yes. No other test would be there. But since this level is no, which means no, this tree needs to be, I mean, this data, this tree needs to be once again, grown so that you can accommodate this data. So in that case, what could be a possibility then at this point, just to accept this data, because there I can make a check. At this point, I will make a check on, say, wind or whatever. I mean, it could be wind or temperature. You can choose any one of them, because we do not have, it is the only data we have, let us assume. Say, if I say this is wind, then if it is, though it is humidity normal, but for wind, if it is, say, strong, then I will say no, and for weak, then I will say yes. So this is one possibility. Okay, just to take care of this part. Because earlier, I think there was a case when, so we have to see the data, and for with respect to that also, we need to consider that data. So let us see what is the result. So yes, we can have something like this, right? The same way as I was telling you, that the tree could be grown and this tree will be consistent with that data. So now, so which means that this example just shows that any data training example set, if you take, and if there is no contradiction in the data, in the sense that the same tuple, same combination should not have two different results. So there should not be any training example where the same combination will have the same different results. So that is the contradiction. So if that contradiction, we are assuming there is no contradiction in your training examples. But no, there could be errors, which means without contradiction also, there could be error of labeling, because you do not have the complete information. Now, here, as you can see that the tree has grown because of this. So how to handle this situation? How to take care of overfitting so that no, you get a hypothesis which is uh, appropriate, which is neither underfitting nor overfitting, right? Which is appropriate at certain. So how do you say that kind of decision tree? How do you get that decision tree? So there are the two basic approaches to avoid this kind of overfitting. One approach is pre-pruning approach. That means whenever you are growing, you are trying to expand those nodes which are covering maximal set of training examples, which means you are not expanding every possible nodes. If you find under a node the corresponding set of associated set of training examples, if you find it is not sufficient, number is not sufficient, you can live with that situation, because with a small amount of data, statistics is not very reliable or not very robust statistical estimate. So that's why just by looking at the size of the training, for example, in this case we have only one training examples, and we can just leave it. We can leave it. We can say that we ignore it and we don't expand. And what you do in that case, it is the majority of the levels that we will be leveling to that part. So it actually will be living before that itself. So that is what stop growing the tree at some point during construction, when it is determined that there is not enough data to make reliable choices. And in that case, as I mentioned, as a policy, we can consider that since you are not growing, you are making it a leaf node, but there are mixed levels still. There are mixed training examples with the examples with mixed levels. So that's why you have to assign one level, and it is the majority of the levels. But as post pruning strategy, what it does, it actually uh, it allows overfitting. That when it grows a tree, decision tree, till you make the training error 0. That first you derive a tree which is an overfit over the training examples. That means you get a 0 error tree. But then you try to find out that what are the nodes which could be pruned from the tree, but which are also giving. That means, as I mentioned, the indications is that if you suppose you have also a test data set. So in the overfit case, you can find out that if you run that decision tree over the test data set, if you predict the levels, then you will find the error is significantly high. Error is quite high, quite significant. So because of the overfitting, you will find that. Now since you are in that situation, so what you can do, you can prune certain node. Let us consider you can prune. You can prune randomly any node. That means pruning of node means all the nodes under that in the subtree, which is rooted at that node, all of them are pruned. That means all the associated, because at every node you have the corresponding associated training samples. So you just consider that, and again you apply the same policy of leveling. That means the majority leveling with respect to that, because you are making this node as leaf node, you put that class level which is occurring most frequently, right? So that level you put. So now this has become your model. Now you apply this model over your test data set. Now check whether actually your generalization error, that means the test error, is improving. That means it is becoming lower. It is becoming lower with respect to the error that you had with the previous tree, whatever previous model you had. If it is lower, then you select this tree which is lower tree. You preferred that tree. Now the order of pruning will also affect this because you are doing it greedily. So you may consider uh, you are checking each and every node, every candidate node. Most likely there, because to reduce your computations, maybe you can make some kind of bottom-up search because that is more practical. From the bottom-up traversal, you identify those nodes which are just above the leaf nodes, and then you go towards root node accordingly. And you find all candidate nodes, such intermediate nodes, uh, for which, after pruning, which one is giving the maximum reduction of test error. So you take, that is your next stage of model, and you repeat this process. You repeat this process till your test error is not improving, till your test error. So till the test error is getting minimum, I mean, it's a kind of monotonic movement. So it's a greedy approach, as you understand. So we'll just have a little more discussion on that. So this is what, grow the full tree and then remove nodes that seem not to have sufficient evidence. So what are the evaluations? I just mentioned that with respect to test samples, you can do it. That is called cross validation. Now that is not the only evaluation method. There are other two methods that is also described here. So briefly, I will just mention them. So in cross validation method, you should have a validation set. You should have a validation set, which was, I was referring at test set, that you should consider it as validation set here. There is a little difference between validation and test. I will discuss them later on. But for the sake of this discussion, let us consider that whatever training examples you have for training the model, you partition it into two sets. One is the validation set, which is called here holdout set. Okay, and that set is used for estimating the generalization error. And over the training set, you are growing the tree and you are fitting the tree with respect to that training set only. And after that, you are recursively pruning or greedily pruning the intermediate nodes of the tree by checking whether your error on the validation set is lowering. Right? You go on doing these things, and then you will get the tree. And there you can consider possible candidate for the, what is the choice for the pruning, which node is your choice for your pruning. That is one thing you should consider. Now there are techniques for statistical testing is also there. So I'm not detailing out, but here the idea is that here you are trying to see that the kind of tree, your decision making process that you have obtained, whether they occur by chance, randomly, I mean by chance they have occurred, or there is an order. So I'm not detailing, so let us not go into details, but this is the kind of statistical approach. um, it's kind of hypothesis testing basically. The hypothesis testing has certain kind of probability distributions in mind of the hypothesis, and if you can show that with respect to that distribution, the occurrence of your hypothesis, so it is in the hypothesis space itself, occurrence of that hypothesis is not random, right? Is not random. It is a kind of it is basically kind of outlier of that. So we have a random distribution, so it's not random. Then you consider that is significant. So that is a strategy. And the other strategy is minimum description length. This is considering the overall size of the tree. I mentioned maybe in the last class also. So what you should consider that while pruning the tree, you are reducing the size of the tree. So that gives you the description. So a tree has a description in the encoded space. And when you are reducing any node, so naturally description length is going to be minimized. And you can see that that this complexity is smaller than remembering the exception. So there are two things. One thing is that uh, what you can consider that those outliers are exceptions. So you don't try to that. So which are the set you are going to use for splitting the tree? You simply consider that you are remembering all their levels. So whenever that condition comes, first you consult those lookup table kind of thing, those conditions, preconditions. If you find them, you use that level. Otherwise, you go for the decision tree, based on prediction. Use the decision tree model. So this is the idea. So the size of your model becomes the size of that lookup table and size of the decision tree. So when you prune a tree, it will have both the things. That means it will reduce the size of the decision tree, but it will increase the size of the lookup table. You are adding more data for which you have to remember. Right? This is the total size of your hypothesis. Right? So at which level of pruning you are minimizing it. So that is which level of pruning. Pruning of a combination of pruning, you get a minimum description length. So that is the approach. Usually cross-validation is easier to understand and implement. So I will be just considering this. The partitioning, as I mentioned, partition training data into grow set and validation set, build a complete tree for the grow data, and until accuracy and validation set decreases, which means error, error is also until it increases at that point. For each non-leaf node in the tree, temporarily prune the tree below, replace it by majority vote, test the accuracy on the validation set. Now, once again, it considers each non-leaf node, but no, you can reduce the computation by, again, readily choosing, some of the candidates from the bottom, up manner. So permanently prune the node with the greatest increase in accuracy on the validation test. So it uses less data to construct the tree. Why less data? Because the training data itself you have divided into two sets. So that has reduced the number of training examples for your model building. So as you know that number of examples, if you reduce the number of examples, then the getting the appropriate hypothesis, the target function is the probability of that getting that thing will be less, because we have discussed in that probably approximately correct hypothesis, right? So that in that learning, PSC learning, we have seen that how number of training examples are related with respect to the probability of getting there it is epsilon exhaustive hypothesis space, right? So yeah, any question?
Sir, is this a post pruning or pre pruning process?
No, this is post pruning, na? Cross validation approach. It is written here also a post pruning. This process, huh? You see? Okay. Because you are whatever you are doing after pruning, you are checking the accuracy. So there is a validation set on which you are checking the accuracy. So on the training set, you are growing the tree. On the training data, so in the grow set, in the training data, there is a grow set on which you have developed the tree. So once the tree is developed, then you are considering a node of the tree, and you are pruning that node, you are removing that node. Now with respect to this model, and also replacing that, but that means you are basically making a node leaf node. Pruning, this means all the subtree is being pruned. So this is a subtree and it is pruned, and this node has been leaf node. So this is a leaf node. Actually, it is not removed in that way, it is a leaf node. And label means whatever number of samples are associated with this subtree, the majority, most frequently occurring labels that would be associated with this leaf node. Now this has become your new model decision tree. So you find out what is the accuracy with respect to this validation set. You find out how many times it is correctly labeling and how many times it is not labeling, and accordingly you can find out the accuracy. So if it is an overfitting, you will find this accuracy is increasing. This accuracy is more than the accuracy of the previous model of model of deeper tree. So you should accept it. Now the question is that there are many options here at this case. Many other nodes are also there. Which node you should select? So you should select that node where you have the maximum reduction, maximum increase of the accuracy. And you go on doing these things, this operation iteratively, till you come up at a situation where there is no increase of accuracy. Actually, it is decreasing. So you should take the model, previous model, whatever model you have derived at the previous stage, you take it, you accept it. Is it clear?
Yes, sir.
Okay. Right. So you can also see that this approach, this post-pruning approach, there is also another method which is called rule-based pruning, right? So we can do it for rule post-pruning. So what it means, I mentioned earlier also that a decision tree, each path of the decision tree can be considered as a rule, right? Because they are all in each path you have the conjunctive literals based on the attributes value. You have the conjunctive literals, and finally the value of the leaf node, that is your corresponding result of the expression. So if I say rule, we say that conjunctive literals, that expression, a Boolean expression, is the antecedent part, and the corresponding value is the consequent part. So you can get all these rules, and then what you do, you can prune the rules. Means you can prune the clauses of antecedents and check once again what is the performance. So instead of doing pruning over the tree, you are doing pruning over the clauses itself. And then after getting all these things, then you can convert them into an either in a decision tree, or you can keep it as a set of rules and apply it. So it is mentioned every leaf node has a rule. Prune each rule independently of others and remove various preconditions to improve performance. So sort final rules into desired sequence for use. So once again, you have the rule base only. So you are not getting in the form of a decision tree after doing these things, but you are reducing the overfitting by removing those clauses. So one of the examples of rule here, you can see, I think these labels are missing. Humidity is high or normal. One of these is no, another yes. Wind strong or weak. One of these is no, another is yes. Right. So it is missing in my diagram. So anyway, let us see. So if outlook is sunny, humidity is high, then play tennis is no, which means in this rule here it was no, and then this is yes. Okay. Similarly, I think this is no, this is yes, because the way convention we are following by denoting that. Anyway, so let us consider that. So, so this is one rule. Similarly, this is another rule of the same. No, if you consider these two leaf nodes, then for each leaf node, you have this rule. So this is one leaf node, which level n. This is another leaf node with level y. So this path will give you this rule, and there are two clauses. So what you should do, you can consider all the set of rules. Similarly, you can consider another rule is if outlook equals overcast, then play tennis equals yes. Then if outlook equals rain, wind equals strong, and wind equals strong, then play tennis equals no, and outlook equals rain and wind equals weak, then play tennis equals y. So there are 5 rules. You can see there are 5 rules. Now you consider each rule, and then you start pruning one of these clauses. Suppose I prune this. So it is same. Instead of applying decision tree based classifier, if I apply just simply rules. So what I will do, given a training example, I will consider each rule, and wherever this is the antecedent part, right, I was talking about. This is the antecedent part, and this is the consequent part of a rule. So wherever antecedent part is satisfying, I will basically use the consequent part for leveling, for predicting. So that is simple. And there should not be any contradictions among these rules. I mean, because your decision tree also is a contradiction. And if you don't get, no, it is not satisfied of the any kind of rule, no, you do not have any decision in that regard. That is also a situation, as you can see. But anyway, let us consider that no, for every situations, you will have this, because no, you are for every attribute you are exhausting these things. So you should have all the situations should be covered in that way. Now, if I remove this, as I mentioned, take this rule and say remove this clause from that rule. So it becomes only if humidity equals high, then plate tennis equals no. Then you see from your training examples, how many of them are getting satisfied using this rule base, and how many of them are wrongly leveled, because you'll be predicting and you will see your training data, given training data you can compare. So that is your performance. So if you find your accuracy is increasing, then you go for no. I mean, it is also validation set. You should do it on the validation set once again. Then you go for this removal of this clause, and this is your new rule base. And you go on iterating this process till once again your accuracy is improving. I mean, decreasing. So this is prune preconditions and evaluate. Now, I mentioned about ID3 algorithm, and where we have considered the attribute sets should be of discrete value or discrete attributes. But you know that you could have situations where you will have continuous valued attributes. So you require some extensions of that basic algorithm. So you have to modify it. So one thing is that continuous valued attributes. Then other thing would be that an attribute with many values. So even if it is discrete, but there are too many discrete values. Now that would make the process, no, you need to do something more, because you will find that this kind of attributes which have more number of values, they will be preferred. There will be a bias to choose them among the candidate sets, because they have more number of attributes. So it is likely that if you choose that attribute, the entropy what you get at the part entropy over the partitions, average entropy over the partitions what you get, that is going to be small. And it's a kind of it is nothing to do with actual data distribution, etc. It is the nature that it is a its number of values itself is so high. So it is by that it is giving that kind of giving that kind of feature. So you have to take care of that. You have to normalize with respect to this, that if you have many attributes, many values rather, so there should be some normalizations. There should be some level playing field between two attributes. One is with many values and another with less number of values, small number of values. I will come to that, how to handle that. Then training examples with missing data. So we have always considered that every training example is having levels, etc. But there could be some training examples because of your in the practical situation, sometimes all the measurements may not be available. You may have partial measurements. You may have outcome, but you do not know certain attribute value. We call that missing attribute values. That kind of training examples. It is not that every training example should have attribute value, or it should have values for all the attributes which are being considered for that example. But in some cases, no, you may not have. So what to do with that? And there could be certain attributes which are very costly with respect to the measurements, for example. So if you use those attributes, then it would be expensive in different. So that's why those attributes may not be preferred. So if you get another model which avoid uses of that attribute but get relatively similar kind of results, even though its performance may be poorer, but we may prefer that kind of model because no, the cost of using that model would be less, right? So this is one situation. And then other thing is that no, we have discussed about particularly one kind of impurity measure, that is information gain. That is the measure we have used. But no, there are other impurity measures that is also used, so we can discuss. So in this way, you can have various modifications on the base algorithm of ID3. There are also other kind of tree which is similar to decision tree. In a structure, it's a tree, but it's a regression tree. So what it does, the decision making process is same. That means at every level you are checking certain conditions, equality of certain attribute value, or if it is a continuous value, then the range of attribute value, interval of attribute value you are testing. And then your final outcome is not the class level, rather your final outcome, once again, like a regression problem, it is basically functional mapping from one domain to a functional value in the real axis, in the real value. So your final outcome would be some real value.
Hello, sir.
Yeah.
Sir, can we have one model or one algorithm that can take all the factors that we have discussed in previous slide? That one model we can develop or that will consider all these factors in one algorithm.
I mean, how do you do that? See, when you are incorporating certain modifications, you may also accept the other one. Is it difficult? You can consider this model in this condition and this model in this condition. Then in that way you can integrate them. Okay. But the question
Yes,
is that
yes.
no, that would increase your. It depends upon context. So making anything very general is not always preferred, because in your context, if you are exploiting the context, then you may get a more efficient algorithm and technique, and your result would be better. And since you are restricting, you are working on under that context, so your performance will be improved. So you have to consider that also. So how do you handle continuous valued attributes? Now, this is a bit straightforward. What we do, we just discretize the attribute ranges. I mean, the value ranges, we just discretize. So you consider the discrete values. That means the intervals. You are discretizing them in intervals, and each interval is represented as a discrete value. So that is what we do. For example, temperature, we can consider the temperature as a continuous valued attributes. There are so many values you can see, but you define discretize it into two ranges, for example, high and low, or you can discretize it into multiple intervals also, say low, moderate, high, or something like that, as many as scale you require. But these are all discretes, and then use those discrete representation. So now temperature has become a discrete variables. Each one is representing certain levels of temperature. So now they become your attribute value and use them in your decision tree. So this is one particular example. Now choosing the proper intervals based on your training data, that is the question that you need to address here. So which one you should choose by looking at the distributions you may choose. For example, you can choose these two such levels, and you can see that with respect to temperature, you will get three partitions which are pure partitions, at least. So these are certain things in your technique that you need to you need to consider when you are choosing the discretization with respect to class distribution itself or level distribution itself. So that is what chosen by information gain function. So that is, so there also you can use information gain by choosing that level which is giving maximum information gain, or you can have more than one threshold and you can look at the information gain. Once again, as I mentioned, that if you have too many values, attribute values, that would be preferred if you use information gain. So there would be other ways to handle that. So I hope this is clear that how do you consider how it is making the information gain. Right. So basically, you have possible candidates of thresholds, and you find out where you are having more information gain, and choose that thresholds in that way. Now, let us come to that this particular scenario when you have attributes with many values. So in that case, as I was mentioning, that information gain will be selecting because your when you are partitioning them, your partitions will be small, usually, of the same data, and then the corresponding entropy is likely to be also smaller, and the average entropy would be smaller. So, so this is one example, say birth rates, and that's what it likely to discriminate well on small sample, but poor predictor on unseen instances. So what you should do in that case, you should compensate. You should compensate with that. So there are measures to do that. So the measure is that you are dividing it. So that information gain, what you are finding, you divide with respect to the entropy over the class distribution on the attribute space. So it is the entropy of the class distribution over the attribute space that you are considering. You see that this is exactly what you are doing, and that becomes your corresponding normalizing factor. So if you have more number of attributes, then it may be equally likely that the samples are over that values, the partitions are having similar, partitions are having a smaller size, but their numbers are same, almost they are similar size, though the size is smaller. But then you see that your entropy would be high, because this is what you are doing, you are considering here. So this is what measures of entropy from distribution in attribute space. That is the split information, that is the normalizing factor. So this is penalizing the high number of partitions. Now this is the second scenario. That means when you have the many valued attributes, then you are doing that kind of normalization. When you have unknown attribute value, that means some attribute value is missing, and then what you are doing. Now there are again different approaches. So when you see that at a particular node, because the point is that how do you consider, how do you evaluate the performance of that attribute in terms of this information gain or normalized information gain? How do you evaluate them? Because they are since the attribute value is missing, you are not able to get into that kind of partition. So what you should do in that case, there are various things. Let me tell you one by one. So use training examples anyway, sort through tree, and when the node n tests A, assign most common value of A among other examples sorted to node A, which means whatever examples are associated with that node. And now the next stage of splitting, when you are choosing attribute A, since for some training examples you do not have the attribute value which are associated, so you can enforce certain attribute value there. One possibility is that, one option is that you choose the most frequent values among that number of examples. what is associated with that node. So this is what you assign most common value A among other examples with same targeting value. So either you choose, or also other thing is that no, you can consider two classes or three based on the target value number of targets. If there are binary levels, there would be two such target values. Now for each class, you separately find out what is the most frequent value of A, and then you assign it. So depending upon target levels, you are assigning them. So this is the second one that I talked about. The third one is that you randomly you assign a value, but that probability should be the probability of the, so you consider the probability distribution. Earlier you were only considering the most frequent value, but now you may consider a probability distribution, and according to that probability distributions, with certain probability, you assign a value here. So assign fraction pi of example to each descendant in tree, right? So so that no, your fraction pi of example, I mean, this is a bit detailing is required. So, but no, you are choosing with probability pi that assignment, and classify test instances with missing value in same fashion. So even in the same fashion, your test instances are also classified. That means in test instances also, if there are missing value, you have to choose the most frequent value there. I mean, the same fashion means already you know that what value you have assigned for the missing value. You should note it at that node. And if you really come up with the situation where that attribute is missing, so you should do that. Otherwise, no, you have to consider the most frequent values of the attribute. Now, attribute with costs. This is another thing where I mentioned that though sometimes some attributes are giving good partitioning with respect to reducing, having larger information gain, but what happens that they may be very costly in terms of measurements, etc. Say you consider the medical diagnosis. Now you have the different kinds of tests. So one kind of test will cost, say, as you say, $150 or rupees. Other cost say 5 rupees simply. So in that case, the pulse checking, basically pulse checking a blood test. So in that case, if you can do most of the tasks using pulse checking, we may prefer that. But no, in your model, you have to select one of them. So what we do, we should learn a consistent tree with low expected cost. That is what we are trying to achieve. So the gain is again normalized by cost. So there is certain, so those costs are also given. So there are certain model for that. So the information gain is normalized in this way and then compared. So there is also another model where the cost is normalizing in this fashion. So these are certain models people have explored and tried, and they have found that these are recommended models based on empirically after empirical study. Now this is about other impurity measures that I was mentioning. So far we have discussed about only information gain and also some variations of normalization on top of it. But there is another impurity measure which is known as, say, Gini index, and this is also in one way it is trying to measure that whether a node is pure or impure. So if it is pure, then this then the information would be low. Like entropy, information gain would be low. Information would be low. Entropy would be low. Like Gini index would be low. And if it is impure, then it would be high. So after applying an attribute, so this is one definition of the Gini index. As you can see that here in this case, I is the level or class. So you are simply what you are computing. If I consider this factor, it is expectation of this factor. As you can see, you can consider it is a kind of, what is the probability of error? Suppose I select a class level, and since class level occurs with probability, class level I occurs with probability I, so the error would be with 1 minus probability I, this error occurs. So overall, what is the occurrence probability of error? So if the weighted probability of error would be pi into 1 minus pi, and Gini index is basically expectation of this probability of error. This is expectation, because this is a probability distribution. Expectation of the error, right? So expected error rate. That is what is Gini index. So when you have a particular attribute, you choose a particular attribute A, and then you look at the induced partitions of that attribute. So that means for each value, you have the induced partition, like the way you have measured entropy. Then in this induced partition, sorry, what is the distribution of class levels and what is their Gini index? So you compute the Gini index and then take the weighted average of that Gini index. So that is what is this expression? No, this is that expression. So as I mentioned, Gini can be interpreted as expected error rate. An example is given here, figurative example. So let me explain you a little bit about this data. See what we are getting, we are showing each example with 3 attributes. They are color, they are border, they are dot. Now you consider this particular, say, sample, each sample. What are the attributes? Color is yellow, border is, I think they have a border. It is not border. Border is, there is a, it has a border. Either it has a border or it does not have a border, and it has also a dot. That means dot is yes. These are the attributes. The value is yes or no. Border value is yes or no. Color value is red, green, or yellow. Is it clear? And what are the classes? Classes are either triangle or square. They are shape. So this training example, if I convert it into textual form, I will write, this is attribute color is yellow, then border yes, and dot yes. Sorry, color yellow. Border yes, dot yes, and what is the label? Say label is here in this case square. So label is S. Is it clear? So each sample you can, from each sample you can get this kind of training example. So how many are there? You have 4, 7, 8, 11, 14. There are 14 samples. Now we are trying to compute the Gini index based on different attributes, say attributes of color, attributes of border, etc. We are considering that. Okay. So in that case, see, I will just because I have only a few minutes left, so I will give this example. Then today I will stop here. So if you compute the Gini index of the whole set, so what should be the Gini index? You have Gini index should be over the class distribution. So what is the probability of square? It is 9 by 14. Probability of triangle is 5 by 14. Then the Gini value, as per our definition, is pi into 1 minus pi. Now, since there are, you can just simplify in this form because there are 2 classes. That's why you just, it is the same. 9 by 14 into 5 by 14 plus 5 by 14 into 9 by 14, as you can see. So your Gini index is 0.46. So let me stop here. In the next class, now we'll discuss tomorrow. We'll discuss we'll continue this discussion where we'll show that attribute induced partitioning, what should be their Gini index. Naturally, the difference of this Gini index is the gain. We can call it a Gini gain, like information gain. And based on that Gini gain, we can choose certain attribute. Which one is the gain is higher, we'll choose that. So let me stop here today, and let me also take your attendance. Okay, I hope attendance is taken. Okay, so any quick question? Fine. So we'll meet tomorrow again in the morning. Thank you very much.